Okay, I'm used to saying good morning, everybody. I guess I'll say good evening, everyone, today. I'm subbing again for Chase. More details about when he's coming back to come. I'm not really informed on whatever's going on. So I'll be teaching today's lesson, and it's just going to go as normal. Look out for some updates on what's going on with your homework and that sort of thing as well. I had one student email me about their exam score. Is that student present today? Okay, maybe they're going to watch the video. We're working on getting all this sorted out. So for now, focus on watching the lectures and learning the material that I teach today. So last time, if I recall correctly, we learned some derivative rules. So let me actually go back to that page. I think it was 3.1. So we learned about how to do the derivative of a constant. Did I start the? Yeah, okay. We learned about how to do the derivative of a linear function, a sum or a difference, and a constant times a function. And we had a whole bunch of practice on all sorts of different functions, on how to use those rules. We also, one second. We also talked about the power rule, okay? So we know how to do the derivatives of things which look like x to some power, or maybe some number times x to some power, or sums of things of that nature. Okay, that's what we've learned so far. So today we're going to expand our understanding of things that we can do derivatives of to a larger class of functions. You typically teach these lessons in a 50-minute class period, so I'm going to try to go through 1.5 lessons maybe today. So that's what we're going to do. So we'll start with 3.2. And let's warm up by trying out some of these problems. Okay, so take a minute or so to try these 4 problems. And try to do these derivatives using the rules that we learned in class last time. And then maybe I'll ask for some volunteers to help me out with solving them, and we'll solve them together. Would anybody like a little bit more time to solve these? Okay, let me ask first, easy question. Which of the 4 did you think was the hardest? No wrong answer here. Okay, everybody seems to think D was the hardest. I suspect maybe C gave some people some trouble as well. A little bit tricky there with the square root. Oh, no. Seeing heads shaking, maybe that was easy. Okay, well, let's do them together. Who can tell me what's the derivative of part A going to be? X squared plus 4. Yeah, it's just going to be 2x, right? The 4, when we do the derivative of a constant, it's just 0, so that part goes away. We can use the sum rule to just say that the derivative of this thing is going to be the sum of those two derivatives. So the derivative of 4 was 0. Oh, maybe I'll write that in here, kind of like a plus 0 there. The derivative of x squared, we use the power rule. The power comes down front and we multiply it, reduce the power by 1. That's how we get 2x there. Pretty straightforward. Next one's just another application of the power rule. We just get, 6x squared minus 7. I think I did that right. So the 7x term, we apply the power rule again. The x to the power 1 became x to the power 0. Okay, so that's why we wound up with just 7 on that part. The other part, we again just multiply down the 3 from the x cubed, reduce the power by 1. Okay? Great. All right, I think that C was a little bit more complicated. We should first try to express H in a rule-friendly way. What should it look like if I want to use one of my rules on it? Can I rewrite this in a rule-friendly way? Yes? Yeah, x to the 1/2. And if I do its derivative, what do I get? Yeah, 1/2 x to the negative 1/2. And if I wanted to write it in a pretty way, I might write it like 1 over 2 root x. Because a negative 1/2, we would put it down to the bottom as a positive 1/2. Once it's in the denominator, we'll just replace that 1/2 by a square root. That's just another way of writing it. All right, last one. Again, I need to write this in a rule-friendly way. Can somebody help me write this in a rule-friendly way? What should it look like? Yeah, 2x to the negative 2. And I could kind of write this last part if I wanted to make it really clear what I'm doing. I might write it as 1/2 times x. Okay, just to remember that dividing by a number is the same as multiplying by the reciprocal of that number, which is why I can just go ahead and use the rule that I have for multiplication by a constant. Okay, so that rule kind of encompasses division as well. I can just take that 1/2 out front and think of it as being multiplied by something. Okay, great, and now I just apply the rule as usual. This will become negative 2, well, 2 times negative 2 times x to the power, what should the power be? Okay, negative 3 plus 1/2. So all in all, I get negative 4 over x cubed plus 1/2. So that was just a review of the things that we did last time. Any questions about that? No questions? Great. All right. We are gonna... What are we gonna do here? Okay, I'm supposed to talk about these rules and chain rule today. I'm going to alter some of these problems for our purposes, okay? First of all, we're going to leave this top rule for later, okay? We're going to leave that rule for later. And I'm going to change this rule. We're going to talk about not the derivative of e to the kx. We're going to talk about the derivative of e to the x. And we're going to talk about the derivative of ln of x. We're going to include these functions now into our rules, and then we'll talk about chain rule, and then we'll come back and talk about the derivative of a to the x or e to the kx. That's the order that I want to do it in. So the first thing is the derivative of e to the x, and it's the easiest thing that you could possibly imagine. The derivative of e to the x is, drumroll please, e to the x. Bam. Okay, so the derivative of e to the x is just e to the x again. And that is the really fascinating thing about the number e. In fact, this is how the number e was discovered. They didn't first come up with e and then find out magically that this was true. They searched for a number that made this property true, and that's where e actually comes from. Okay, pretty amazing. If you have a deeper understanding of calculus and what the rule that we're going to learn later in class today, this is really, really freaking amazing. Okay, I hope that you're impressed. The next rule is the derivative of ln of x. So if we want to do the derivative of ln of x, it's not quite as simple, but it's pretty simple. It's just going to be d dx of ln of x equals 1 over x. Okay? Great. So, two new derivative rules. I want to remind you guys that this notation here, when I write d dx and then these parentheses, that kind of means do the derivative of. And whatever's on the inside is what I need to do the derivative of. Okay? So let's modify some of these problems. I'm going to get rid of that piece right there. So imagine we had 2 plus 5e to the x. I'm going to need to use one of my new rules and a couple of my old rules in order to do this problem. Okay? The old rules that I'm going to need are multiplication by constant, okay, because I'm taking e to the x and I'm multiplying it by a constant. I'm also going to need the sum rule because I'm adding two things together. And I'm going to need to use the rule which tells me what is the derivative of a constant. So those are the old rules that I'm going to need to use. I need to use those old rules in combination with the new rule we learned about the derivative of e to the x. So let's write this out very carefully. If we want to do d dx of 2 plus 5e to the x, this is the same thing. By the sum rule, we can just do the derivative of 2 and then add the derivative of 5e to the x. That's the sum rule right there. Now I can use the derivative of a constant rule to get rid of this 2 here. It just becomes a 0. And I can use the multiplication by a constant rule to pull that 5 right out of this d dx here. So I'm going to get 5 times d dx of e to the x. So far I applied the sum rule to split this thing up into two pieces, two different derivatives, and then I used the derivative of a constant rule to make the 2 go away, and then I did the multiplication by a constant rule to make this 5 come out. So now the last thing I need to do is just use the rule that we just learned, which is I need to take 5 and multiply that by the derivative of e to the x, which we just learned is e to the x. So this is just going to be equal to 5 times e to the x. And that's our answer. Okay? Any questions? Fairly straightforward. Okay, if you do have any questions, feel free to interrupt me at any time. Sometimes I kind of drone on a little bit. All right, let's try another one. Get rid of that part right there. All right, let's try this one. We want to do the derivative of 8x squared plus 8e to the x plus 8. Okay, who can tell me how I'm going to solve this derivative? or maybe some of the rules that I'll use along the way. Just give me some kind of information about, to get me started on this.
For the first part, you did 16x.
Yeah, the first part we get 16x. That came from the 8x squared by the power rule. All right, we know we're going to have a plus something and then a plus something. What should go on the end here, which comes from the derivative of 8? 0. Okay, everybody's comfortable with that one. How about the middle?
8x.
Yeah, 8e to the x. So, kind of amazing. The derivative of 8e to the x is just 8e to the x. Okay? So, the reason that's true is because d dx of 8e to the x by the multiplication by constant rule is equal to 8 times d dx of e to the x, which is equal to 8 times, well, the derivative of e to the x, which is just e to the x. Yes?
Is that like it for if it was any number?
Any number, yes, absolutely true. So if a, for example, is some number, the derivative of a times e to the x is going to be a e to the x. What's not going to be true is if we had some b here, if we had some number up here, that's going to mess things up a little bit. But we'll talk about that in a few minutes. As long as it looks like this, this is true. The derivative of a times e to the x, so a could be pi, negative 1 million, positive 1/2, who knows, could be any number. Alrighty, but not something like x. No functions allowed to be a. Okay, let's, let me pause and ask. These two questions had to do with the derivative of e to the x. Are there any questions so far? Okay, I'm going to save some of these other problems for later. I'm going to talk about the chain rule, and then maybe we'll switch back to this note set and do some of those. For now, ooh, perfect, we can do this one. Let's try a. Okay, everybody take a minute and try a on your own, using the rules that we learned, which I'll just write them here to remind you what they were. We said that d dx of e to the x is e to the x, and we said that d dx of ln of x is equal to 1 over x. So now we want to find f prime of t, where f of t is this function 5 ln t plus 7e to the t minus 4t squared minus 12. Okay, so I'll keep the rules on the screen so that you can remember what they are. Okay, would anybody like a little more time? So everyone has an answer? Okay, somebody besides my best friend, can you tell me what this derivative is going to come out to be?
said the derivative of f of t is negative 8t plus 7et e to the t plus 5 over x.
7e to the t plus, sorry, what was, oh, I see. Okay, you rearranged it a little bit.
Yeah.
Okay, you said negative 8t plus what now?
Plus 7e to the t, and then I don't know if this is right, or I said plus 5 over x.
You're nearly there. Not 5 over x. What should it be?
I mean 5 over t.
Yeah, 5 over t. Okay, perfect. Thank you very much. So, this is what we got. So let's walk through what really happened here. First of all, the 12, it went away when we did its derivative. It became 0. The 4t squared, that should be familiar. Power rule, multiply down the 2. All right, 7e to the t. We just learned that any number times e to the x, or e to the z, or e to the t, or e to any variable, if we take the derivative with respect to that variable, we'll just get back the same exact thing. So this thing stayed exactly the same when it came down here. The last thing that we needed to do was the derivative of 5 ln t. We used 2 rules to do that derivative. The first rule is multiplication by constant. We can leave the 5 alone and just let it float out front, okay? You could have written that maybe like this. 5 times the derivative, we'll write d dt, since we're doing a derivative with respect to t, of ln t, which would then be 5 times 1 over t. And our friend here did 5 times 1 over t. He knows that we can just write 5 over 1, right, and multiply straight across. 5 times 1 is 5, 1 times t is t, and get 5 over t. Okay, very good job. Thank you for that. All right, let's have some thumbs. Thumbs up if you totally agreed and got the same exact answer as our friend. Thumbs sideways if you got most of it. Down if you were like totally off. Let's have a thumb from everyone, please. Okay. All right. We'll move on. Oh, man, another great problem. I like this one. Let's talk about problem C together. The reason I want to talk about it together is because there's a trick in this problem. They're trying to trick us. Does anybody see what the trick is? Yeah, it's the e cubed. Okay? What they're thinking is, aha, I just told students about the derivative of e to the x, which is a function, right? Now, I'm going to try to mess them up by putting in something which looks just like that, but is not quite the same. Why is 4e cubed different than what we've been doing so far? Yeah, what we've done so far is things like 4e to the t or to the x. The key distinction here is this thing right, well, not that thing. I guess we'll talk about this thing right here in purple. That is a function, okay? A function, you can plug in a number and then you get out some other number, right, based on the rule. 4e cubed is not a function. What is it? It's a number. Yes, it's a number. Or a constant, if you want to call it a constant, that's fine too. It's just a number. What do we say about the derivative of numbers? 0. Exactly. So when we do f prime here, this part's just going to come out to 0. They tried to trick us. Okay? So, You can try it on your own. You can go on Wolfram Alpha, or you can use your graphing calculator, and you can type in E, and then the little caret thing for a power, and then 3. You push enter, it'll give you some number like, I don't know, it'll be less than 27. But it'll be some crazy decimal number. But it's just a number, okay? So if we take that number and we multiply it by 4, it's still just a number. So we could write this out as something like, well, why don't I actually just do it? And I'll write it out what it really is. Let's see, gotta turn the phone sideways to do this one. All right, 4 times e to the 3rd power. This whole function is the same as the function 80.3421476928 plus 2.45 lnt. Okay? And if you saw that decimal point right there, I bet you'd know right away when we do that derivative, it's just going to be 0. It's just a number. We do the derivative of a number, we get 0. All right, I think I've beaten that into the ground enough. What are we going to get when we do the derivative of the second part, 2.45 times ln of t? Yeah, 2.45 over t. Little bit unconventional to write a decimal in a fraction. Let's fix it by writing 245 over 100t. That's a little bit easier on the eyes. Okay, so crisis averted. We didn't fall into their trap. Okay, so we did 2 problems relating to e to the x, 2 problems relating to ln t. What I'm going to do now is switch gears and talk about the most important thing you'll learn in this class, probably, which is the chain rule. Okay, so we're going to skip the warm-up problems. No, actually, we're not going to skip the warm-up problems. We're going to do these. We're going to do these first 2. We're going to do A and B. Okay, so let me explain what the question is asking first, and then I'll give you guys a second to try it out, because this is a crucially important skill to be able to do chain rule problems, okay? So, before, you may have done some problems which said something like this. If f of x equals x squared and g of x equals, I don't know, how about I rewrite this in a different way? Oh, this will work, yeah. X plus 7, how about that? What is f of g of x? Okay, this should be familiar. We did, or presumably you guys did a chapter on this. So if we just, what we do here is we just take this whole thing that's g of x, this whole x plus 7, and we plug it right in for x in the function x squared. So we would get f of g of x equals x plus 7 squared. Okay, pretty simple composition problem. We take one function and we plug it into the other one. Okay, so that's what we would do on a problem like this. So what we now are going to be required to do is a little bit different. What we're going to do instead is say the following. We're going to do a different problem. We're going to do the problem if f of g of x equals x plus 7 to the power 2, what are f of x and g of x. Okay? So now what we need to do is look at a composition of functions and decide which one is the inside function and which one is the outside function, and how can I write them. Okay? This is what we're doing now. So, and also, by the way, I should note, usually we don't write the same letter in both ones. We'll write something like z in f. And then we say, okay, we plug g of x in for z in f of z, and we get x plus 7 squared. And I want to figure out what f and g are. So, in practice, what I would do if I was a calculus student, or I'd do it today too, I guess, is I would look for whatever's inside the parentheses. Okay? Whatever's inside the parentheses is usually your inside function. Okay? So, in our case, I would write g of x is x plus 7. I don't like that. X plus 7. And then I would say, okay, if I take x plus 7 and then I do something to it, and in the end I have x plus 7 squared, the thing that I did is what I'm trying to identify. What I did to it was I squared it. So I need f of z to be some function such that when I plug something into it, the result is that thing squared. Well, that's just the function z squared. Okay, so now we're working backwards. So let's take a minute or two to try to identify, okay, we have this is equal to f of g of x equals f of g of x. Our goal is to figure out what f of z is and what g of x is. We'll write g of t, sorry, because it's a t, isn't it? F of z and g of t. That is our goal. So take a couple minutes to try that out on your own. All right, please raise your hand if you're finished. Okay, some people still working. Take a little bit more time. Try it out. All right. If you're struggling with this, don't panic. Okay? This is a skill like any other skill that you have to struggle with at first and kind of suck at, and then after a while you'll get better. Okay, I promise. You know, it's just like, you know, if I want to play tennis like Roger Federer, I'm not going to be able to get there before I hit an awful lot of tennis balls, okay? So, let's hit some tennis balls and try these out. Let's start with A. We've got this function ln of 3t, and what I'd like to identify first is g of t, okay? Like many things in mathematics, I'm going to start on the inside and work my way out, okay? So, what I need to find here is the function that seems like it is being plugged in to another function. Okay, the function that seems like it is being plugged in to another function. Now, what is that function? I will ask you now. Anybody brave enough to volunteer? I heard 3t. That's exactly right. 3t is the inside function. You can tell because it's, well, inside the parentheses. Now, the next step, if I was going to verbalize what it really is doing, I would say, I need to find the function such that if I plug 3t into the function, I get ln of 3t. Okay? So if I take 3t and I plug it into f of z, and I plug in 3t anywhere I see a z, what should that function f of z be? Any thoughts in the far back? Or not super confident in your answer? Yeah, exactly right. ln of z. Thank you. Yeah, it should be ln of z. Okay, so we just kind of decompose ln of 3t into sort of like what's the inside function and what's the outside function, right? That's kind of what we're doing here. So, if you struggled with the original problem that I wrote up here about like how to compose those two problems, you may want to go back and review some of those problems. I think you guys have Wiley Plus, right? Yeah, so like there's a section on Wiley Plus that's like read, study, and practice or something like that. I recommend that you go back and try out some of those problems because that composition skill, it's kind of hard to do these backwards problems without a really good understanding of the forwards problem. Okay. All right, let's do B a little bit faster. What's my inside function here? Yeah, 2t plus 3. And it's being plugged into f of z, where f of z is what function? You want to go for gold? Do you have the outside function too? You're close. Very close. No, you're closer with 5 squared. What?
5z squared?
Yeah, 5z squared. So you were nearly there. We just need to have a little bit of a variable there so that we can plug in the 2t plus 3. So 2t plus 3 here in our original equation is taking the place of z. Okay? All right, thank you both for volunteering your answers. You can always check your work on these, by the way, by doing the forward problem again. If they give us this stuff and they tell us to find out what's f of g of t, well, I would get 5, and then I would just, wherever I see a z, I would write 2t plus 3, and then squared. So I'd get back my original answer. Okay, wonderful. We can't be stopped. We're gonna skip problem B. Now we're gonna learn about the chain rule, which is super important. I'll write it down. It's very important. It tells us how to do derivatives of compositions of functions. All right, rule time. The derivative of, remember that's what this all means. Do the derivative of f of g of x. We get f prime of g of x times g prime of x. In Leibniz notation, we would write it like this. We would say if y equals f of z and z equals g of t, then we would say that dy dt is equal to dy dz times dz dt. Okay? Now that is probably like turning your brain into spaghetti, so let's kind of talk about what that means. Dy dt is derivative of f of g of x. Dy dz is f prime of z. But remember, I didn't leave myself enough space here. Z is g of t. So f prime of z is just f prime of g of x. Okay, and then lastly, this dz dt is what we get if we do the derivative of z equals g of t. So that is the g prime of x part. You know what? Let me make this color more different. We'll make it blue. Okay, so those are the corresponding parts in Leibniz notation. Raise your hand if you like Leibniz notation. All right, for those of you at home, nobody raised their hand. I don't think anybody likes Leibniz notation the first time they see it. I kind of like it. But then again, I'm in a math PhD program, so. Okay, so that's the rule, and now we'll try applying it. What this rule really says is if I do the derivative of a composition of functions, first I take the derivative of the outside function, and I plug in the original inside function. Then I multiply by the derivative of the inside function. Okay? It's not super intuitive, but once you do it 10 times, you'll start to get the hang of things. So the first thing we're going to try to do is e to the 15x. So the first thing that I want to do anytime I start a chain rule problem, in fact, let me write this down, the steps to the chain rule problem. The first step to a chain rule problem is figure out f of z and g of x, or t, or whatever. Did I write it with x up? I wrote it with x up there, so I'll leave it like that. Figure out f of z and g of x, the outside and the inside function. That's number one. Okay? Step 2, compute f prime of z and g prime of x. Step 3, plug g of x in for z in the function f prime of z, then multiply by g prime of x. These are the 3 steps to a chain rule problem. So, the first step is to figure out the outside and the inside functions. Let's do that for this equation, y equals e to the 15x. First, I start with the inside function. Are you squinting to see the board, or are you confused?
No, I'm squinting to see the board.
Should I zoom in a little bit? Is that better? Okay. So, e to the 15x. My goal first is to figure out the inside function. I always start with the inside function and work my way out. What do we think the inside function is here? Talking about g. What is the inside function? The function that looks like it's being plugged in to another function. Yeah, 15x. And what is the function which should have a z in it, where I just plug in 15x for z? Yeah, e to the z. Okay? If I have these two functions, f and g, and I plug g of x into e to the z for z, I get e to the 15x. All right, step 1 complete. Step 2 now. Let's go back and see what it said. Okay, step 2 says that we should compute the derivatives of f of z and the derivative of g of x. So let's do that. We've got these two. Now let's figure out what should f prime of z be. If f of z is e to the z, what's the derivative of e to the z? Yeah, just e to the z again, right? That's the easy rule. And if g of x is 15x, then g prime of x, I don't want to insult you by asking, it's going to be 15, right? Okay. So now this is like our box. And our box has all the information that we're going to need to do the last step, which is just plugging and chugging. What I need to do is derivative of f of g of x. Now I know that that is going to be equal to, did I do too many? No, that's enough. That's going to be equal to f prime of g of x and times g prime of x. So what's really going on here, let's color code it. G of x is 15x. I'm going to plug that in for z in f prime, which is e to the z. Then I'm going to multiply by g prime of x, which is 15. So first I take g of x, that's 15x. If I plug it in for z in e to the z, I get e to the 15x. So that was sort of the, maybe, how do I do that even? Is this the right color? I'll circle the whole thing, kind of. That's how I'll do it. So that was all that jazz. Now I multiply by 15. And that's the red part. Okay? So my blue box, it's like my pantry. It's got all the ingredients I need to cook up this derivative. And I just need to put them in the right place in the right order. Okay? Questions about the chain rule or this problem? Yes?
You have to leave it like
I would probably choose to write it as 15e to the 15x. That's probably a better way of writing it. Yes?
Can you go back to those rules quickly? I didn't get all of them.
Sure thing.
Thank you.
Yeah, the rules are first to figure out what f of z and g of x are. So let me see if I can get it all on the same page. You guys all read all that? So first of all, we had to figure out what f and g were, the inside and the outside function. Then we took their derivatives. At that point, I drew the blue box around all of my ingredients, and I decided it's time for step 3, which is plug g of x in for z in f prime of z. That was when I plugged, I can color code this part as well, actually. That was when I plugged the green part. Whoa, that's the wrong one. I think it's the wrong color, too. Okay, the green part, remember I plugged it into the orange thing, f of z, f prime of z, excuse me. And then multiplied by the derivative of g. So that's the color coding of what was going on there. All right. Any other questions? You guys feel confident with the chain rule? Maybe let's do another example and then I'll ask for some thumbs about confidence with chain rule. All right. Ooh, now they're giving us something kind of funky. They're giving us f of x equals this function. And there's something a little bit tricky about this problem, which is in my problem, in my rule here, I used f as the function that was the outside function, but now f isn't representing the outside function, it's representing the whole function. So I'm going to have to switch up my letters a little bit here, okay? So let's do that first. I'm going to have to switch up my letters. I'm going to say f of x is equal to g of h of x. G of h of x. Okay, the only thing that changed here was the letters I'm using. So now if I want to do the derivative of, if I want to find the derivative of f, I'm going to use this rule that's written in the gray box, except everywhere I see an f, I'm going to write a g, and everywhere I see a g, I'm going to write an h. Okay? So what this is really going to show you is just the general form of what's going on with the chain rule, okay? So it's not that the chain rule is so attached to these particular letters. It's just that the chain rule, when we do this derivative, it is derivative of the outside function, where we plug in the inside function, and then we multiply by the derivative of the inside function. All right? Would anybody like me to go through that one more time? A little bit confused by the letter switch? Okay, I'll go through it a couple more times because people are raising their hand. So, in our original rule here, do I want to? Yeah. I'm gonna erase these highlighting things here. Okay. So, let me point out the similarities here. We had the derivative of f of g of x. So in our original thing, the outside function was f, the inside function was g. Okay? And we said that if we do the derivative of a composition of functions, what we get is the derivative of the outside function, where we plug in the original inside function, and then we multiply by the derivative of the inside function. Okay? So I don't want you guys to attach this rule to the letters too much. What I want you guys to think of is in terms of outside and inside functions. Okay? So in our case, we had g as the outside function. That's why I'm color coding it with red, because it's taking the place of f in my gray box. And the inside function was h, which is why I'm color coding it with green. It's taking the place of g in our original function. So this is just to say that if I do the derivative of all this jazz, I should do it in the same way that I do the derivative of f of g of x, except I should keep track of which is the inside and which is the outside function, and then write it in the same way. Okay, so this part, this g of h of x that I just color coded, is kind of corresponding to this part right here. And then the other part is going to correspond to what is the derivative of that, which is this yellow line here. So if we were to color code this part, well, the inside function is h. So the green parts are going to be those guys, and then the red part is going to be, I don't think that's right red, this guy, the g, okay? So that's what's changed here, is we're using different letters, okay? But the chain rule doesn't care about letters. It just says if you do the derivative of a function, what you get is the derivative of the outside function, where we plug in the inside function, and then we multiply by the derivative of the inside function. And it doesn't care if your functions are called f, g, y, q, w, z, anything. Okay? Any letters that we want, we just need to do the derivative of the outside function first, plug in the inside function, and multiply by the derivative of the inside function. Okay, so in terms of our rules now, my original rule was figure out what f of z and g of x are. Let's modify that rule a little bit to fit with our new setup. What we should really say is figure out the inside and outside functions using whatever letters you feel make you happy. Then our goal is going to be compute the derivatives of those functions. And then lastly, we're going to say plug inside in for z in derivative of the outside function then multiply by derivative of inside function. Does anybody, well, here's what I should say. If you really hate switching up these letters, here's what I recommend you to do. Just cross out this F and write some other letter like N. And then say, okay, N of X equals F of G of X. And then you define your F and G as normal, okay? If you really don't like using different letters, you can do that instead. Just to make sure that when you get to the end, you got to go back and say, okay, when I finally figure out what N prime is, then after that, I have to go back and say, okay, that's actually what F prime is. Okay, so you can do that if you're really, really dependent on on the letter system. But I think it's good to just learn the general form. So, okay, I've belabored this enough. Let's actually do it. And we're going to use g of h of x. So, g of z is going to be something, and h of x is going to be something. And h, remember, is taking the place of my inside function. I want to work from the inside out, so the first thing I have to do is figure out what the inside function is. What is it? Three x cubed minus x. Now g of z is the function that if I plug 3x cubed minus x in for z, I get 3x cubed minus x to the power 5. What should it be? Z to the power 5. Let's pause and have some thumbs. Thumbs up if you felt okay about the process we just did. Thumbs down if you totally hated it, and somewhere in between if you're somewhere in between. Okay, I'm seeing several thumbs up, some sideways thumbs. Again, I think this is something that just takes practice. All right, but these are the right ones. So the next step is to figure out what are the derivatives of those functions. Well, the derivative of z to the 5th is just going to be 5z to the 4th. And the derivative of h is going to be 9x minus 1. That should be 9x squared minus 1. Okay? So now we have our special blue box, which is like our pantry with all the ingredients. And now I'm going to take all of that stuff and I'm going to plug it into this thing right here. Okay? So I'll write f prime of x. Well, I just take h of x, which is 3x cubed minus x, and I plug it into g prime of z. So I get 5 times 3x cubed minus x to the power 4. Okay, that was g prime of h of x. Now I have to multiply by the derivative of h of x, which is 9x squared minus 1. Okay? So that is how I get my answer. Are there any questions on this problem? I know this stuff can be kind of confusing at first. All right, if there's no questions, we'll move on. So, we talked about the chain rule. Great. Let's go back now. And as I said, we're now going to give this rule for the derivative of a to the x. I'll write it on a separate sheet of paper. So the next rule is the derivative of a to the power x okay, and I'm going to walk you through the way that this rule can be proven. Okay, just using the stuff that we already know. Okay, and there's one trick that we have to use, which is the fact that e to the x, and ln of x have a special relationship. Does anybody know the word for the special relationship that e to the x and ln x share? It starts with an I. They're inverses. They undo one another. So if a is some number, maybe I should write that. A is some number. then what would I get if I did e to the ln of a? A, just a, yep. So, this is a fact. And that's the fact that we're going to use to prove this rule. Okay, so if I want to do d dx of a to the power x, it's the same as doing d dx of e to the ln of a all to the power x. Remember, ln of a is just a number here. I can plug it in on my calculator, I'll get some decimal. If I take something to a power and then to another power, what do I do with the powers? Do I multiply or add? Hands up for add. Hands up for multiply. We're split about 50-50. Let's have an let's have an example, okay? If I do x squared and I cube that, that's the same as doing x squared times x squared times x squared. What would I get if I did all that? X to some power, what's the power? 6. So, if we take something to a power, should we add the powers or multiply them? 2 plus 3? We should multiply them. 2 times 3 is what we should get. That's how we get 6 here. So this is equal to x to the 2 times 3, which is equal to x to the power 6 here. Okay, so if I take e to the some number to some number, this is the same as doing d dx of e to the those two numbers multiplied. Okay, and now I have something which looks like e to some number times x. Now I can apply the chain rule. This is the derivative of f of g of x, where the inside function g of x is ln of a, which is just some number, times x, and f of x, the outer function, is e to the we'll do it e to the z, and that's f of z, excuse me. Okay, so I know that the derivative should be f prime of g of x times g prime of x. So if I take the derivatives of these two functions, g prime of x is going to be equal to just ln of a, because it's just some number times x by the power rule becomes just that number. Okay, it's just like how the derivative of 3x is 3, or the derivative of pi x is pi. Let me really pound that into your brain. This is a number. Okay, we said that a is some number. If a was 3, I'd take my phone right here, I'd plug in on the calculator ln of 3, and I hit the equal sign. It's going to give me some crazy decimal. All right, so ln of a is just some number. And remember, we have a rule for how to do the derivative of a number times x. We just get that number back. All right? So g prime of x is just ln of a, and f prime of z, this is the easy rule, it's just e to the z. Finally, this is kind of like my blue box again. Finally, I can plug in. I get e to the ln of a times x times ln of a. And I can rewrite this again as e to the ln of a all to the power x. times ln of a. And I'm going to put e to the ln of a back into the form that it was in originally. When I used my fact to rewrite a, I rewrote it as e to the ln a. Now I'm going to use that same fact to rewrite e to the ln a as a. So I get a to the power x times ln of a. All right, kind of a lot of work, but in principle, you can figure out what the derivative of, say, 9 to the power x is. If you know what the derivative of e to the power x is, the chain rule, and the fact that e and ln are inverses. Okay? That's the nice thing about math, is you can prove big results or surprising results using baby steps. All right, so this was all to say that if f of x equals a to the x, then f prime of x is equal to a to the x times ln of a. That's the rule that we just showed. So, for example, if f of x equals 3 to the power t, then f prime of x, that should be an x there, sorry. Then f prime of x equals 3 to the power t times ln of 3. All right, that is the rule that we just learned. All right, I got 3 minutes left, so maybe we'll do one problem here. I'm going to go back to the other set. We'll do this last problem here. Okay, I'm going to go a little bit faster on this problem. In principle, it's great if you can do the chain rule using all of the setup of making things f and g and then taking the derivatives thereof and then plugging into the formula. That's a great way to learn the chain rule. Once you get the hang of it, though, you'll look at something like this and you'll start to immediately see, aha, 1/2 x here is the inside function and e to the z here is the outside function. I know that by the chain rule, the derivative of e to the 1/2 x, well, it should just be the derivative of the outside function, which is just e to the z again. And then I plug in 1/2 x, and then I multiply by the derivative of 1/2 x. So I'll get just e to the 1/2 x. And then sometimes people like to write this kind of notation. They'll circle this and then put an arrow down to show that there was a chain rule going on here. And we'll say times 1/2. The next part, we can see this is another composition of functions. It's x plus 2 being plugged into the power z to the 4th. The way I do that derivative is, again, I just kind of treat this whole thing as z. So I would do 3 times x plus, sorry, not 3. 4 times x plus 2 to the power 3. And then I would chain rule out the derivative of x plus 2, which is just 1. So my answer is 1/2 e to the 1/2 x plus 4 times x plus 2 to the power 3. All right, practice will allow you to do this as well. Okay? All right, that's it for today. If you have any questions, then you can ask me. Otherwise, we're done.
Thank you, have a good day.
Yep, you too.
Do you want me to post the video from today?
Yeah, so actually, you sent the email